Problem 16.87. In this problem, we consider a soldering iron which has a cylindrical tip of 2.5 millimeters in diameter and 20 millimeters in length. With age and usage, the tip has oxidized and now it has an emissivity of 0.8. Assuming that the average convection heat transfer coefficient over the soldering iron tip is equal to 25 watts meter square Kelvin, and the surrounding air temperature is 20 Celsius, we need to determine the power required to maintain the tip at 400 Celsius. So notice that we are analyzing the tip. It is going to be a cylinder that is going to be like this, and then the area that we're going to consider is going to be the surface area plus the actual area of the tip. So we have the surface area, which is pi dl, plus the cross-sectional area is pi over 4 d squared. So the area that we are using is going to be 1.62 times 10 to the negative 4 meters squared. In this problem, we have both convection and radiation. So the total amount of power that is released by the tip is going to be the addition of radiation plus convection. So that's the amount of heat that is going to be lost, that is going to be produced by the tip or dissipated, and this is how it's going to be cooled down by both radiation and convection. So let's start with radiation. Radiation is simply emissivity, Stefan-Boltzmann's constant, the area, the temperature of the tip to the fourth, minus T surrounding to the fourth. Okay? And then we're gonna write the temperatures over here at the bottom so that we have them all in Kelvin, since we're going to use radiation. So the temperature of the tip, it is equal to 400 Celsius, and that is equivalent to 673 Kelvin. The temperature of the surrounding is equal to 20 Celsius, which is equal to 293 Kelvin. And those are the values that we're going to use in here. So once again, the value of radiation, the emissivity is given to be 0.8. The Stefan-Boltzmann constant is equal to 567 times 10 to the negative 8 watts m squared Kelvin to the fourth. The area we calculated to be 1.62 times 10 to the negative 4 meters squared. The temperatures of the tip, so we have 673 Kelvin to the fourth, and then we have the surrounding temperature, which is 293 Kelvin to the fourth. Okay, and then we plug these values in a calculator, and we find that the heat loss by radiation is equal to 1.45 watts. So now we're gonna do the process for convection. The amount of heat lost by convection is equal to the amount, it's equal to H, area, T of the surface of the tip, minus T infinity. Notice that in this case, we're going to assume that the surrounding temperature is equal to the ambient temperature. Okay, and Ts is simply the temperature of the tip. So the convection value is going to be equal to 25 watts m squared Kelvin. The area that we calculated is equal to 1.62 times 10 to the negative 4 meters squared. You could do this calculation both in Celsius or in Kelvin. It's exactly the same, since delta Kelvin and delta Celsius is exactly the same. So we have 400 minus 20 Celsius, and then we find that the amount of convection that we have in this case is going to be equal to 1.54 watts. Notice that the order of magnitude for radiation and convection are very close to each other, and that means that we cannot neglect any of the two modes in this particular problem. So just to find the actual value, the final value is the summation of these two. So Q total is going to be 1.45 plus 154, which gives us 2.99 watts. Okay. It is worth noting that in the problem it says that the tip has been used and damaged and has been oxidized, and therefore the value of emissivity is equal to 0.8. If this had been a brand new tip, the actual value of the emissivity would have been about 0.05. In that case, the amount of radiation, if we do the calculations all over again, it would have been simply 0.091 watts. Okay, and then that means that the total amount that you're going to have, that you're going to dissipate, is going to be equal to 1.63 watts. This is equivalent to a 45.5% reduction in the amount of total heat that needs to be dissipated at the tip.